Before construction of any major infrastructure, engineers must understand the nature and the sequence of the subsurface strata, groundwater conditions, and the physical and mechanical properties of the materials encountered. This is important not only to assist in well-informed designs of stable and safe subsurface infrastructure such as foundations and tunnels, but also for economic considerations, including the cost of over-design. To avoid this, there are a couple of ways that geotechnical engineers determine these conditions. There is bore drilling and rock coring using drilling rigs, which come in various shapes and sizes. There is the collection of disturbed and undisturbed samples for laboratory testing to determine the material's physical and mechanical properties. On top of that, there are in situ tests that can be conducted, like the standard penetration test or SPT, the dynamic cone penetration test, and more. However, there is no one-size-fits-all test for site characterization. The choice of the ground investigation is dependent on hazards, probability of occurrence, and the consequences. In today's video, I want to talk about a specialized ground investigation technique called the cone penetration test or piezo cone penetration test. These tests are widely known as the CPT or the CPTU in the industry. I'll be using these two acronyms interchangeably throughout this video, and I will explain the difference later. This is Chido Chashe, and you are watching Geotechs with Clemens. The cone penetration test works by pushing a cone-tipped rod into the soil at a constant rate. As it descends, it provides a nearly seamless stream of data on the resistance of both the cone tip and the outer sleeve. The first cone penetration tests were conducted in 1932 in the Netherlands. This early version used a 35mm outer diameter gas pipe with a 15mm steel inner push rod. The CPT was then modified into a 10-ton push machine by Delft Soil Mechanics Laboratory in 1935. In 1949, the cone was improved by adding a conical part just above the cone to prevent soil from entering the gap between the casing and the inner rods, which had been a persistent problem in the early versions of the device. Fast forward to 1953. Bergerman added a friction sleeve behind the cone to include measurements of the local sleeve resistance, and for the first time, the concept of friction ratio to classify soil type was introduced. Up to this point, the CPT was purely a mechanical device, and there were no well-established standardized regulations for performing the CPT or analyzing its results. In 1965, Fagro developed an electric cone whose shape and dimensions formed the basis for modern cones, the international standards, and the ASTM procedures. The electric CPT solved the challenges previously experienced with the mechanical CPT. In 1974, CPTs that could also measure pore pressures were introduced. This formed the foundation of the modern-day CPTs and CPTU. The difference between the two is that the latter is capable of measuring pore water pressure. Cone penetrometers come in a range of sizes, with the 10 and the 15 square centimeter probes the most common and specified in most standards. Since the introduction of the electrical cone in the early 1960s, many additional sensors or modules can be added to the cone. This can range from geo-environmental to seismic modules. This right here makes the cone penetrometer a versatile apparatus for ground investigations. One of the biggest advantages of the CPT equipment is that it can be deployed to many locations using a wide range of delivery systems. On land, this generally consists of a truck or a truck-mounted CPT unit, a small anchored drill rig, and even a portable ram set for CPT inside buildings or where there is limited access. Over water, there are a variety of delivery systems depending on the depth of water. Floating or jacked up barges are common in shallow waters, whereas specially designed underwater CPT delivery systems are placed on the seafloor in deep waters. Now, let's talk about how the cone penetrometers work. The cone and the sleeve uses strain gauge load cells to measure resistance to penetration. The two basic cone designs use either separate load cells or subtraction load cells to measure the tip and the sleeve resistance. The penetrometer is a cone tip, a pore pressure transducer for measuring groundwater pressure, a tip load cell to measure the tip resistance as the cone penetrates the soil, a friction sleeve, and a friction load cell for soil friction measurements. All signals are transmitted via an electric cable to the data acquisition unit for analysis and presentation. So, up to this point, we have seen the cone penetrometer mechanism, but how do we determine, let's say, the type of soil or the strength of properties from the tip resistance, sleeve friction, and pore water pressure? You see, over time, numerous semi-empirical correlations have been developed to estimate geotechnical parameters from the CPT for a wide range of soils across the continents. One of the major applications of the CPT is for soil profiling and soil classification. Traditional soil classification systems are based on laboratory-determined physical characteristics such as grain size distribution and plasticity measured on remodeled samples. On the other hand, CPT measurements respond to in-situ mechanical behavior of the soil, such as strength, stiffness, and the compressibility. Unlike traditional methods, the CPT measurements provide a repeatable index of the aggregate behavior of the in-situ soil in the immediate area of the probe. So, how does the interpretation work? In 1986, Robertson developed a soil behavior type chart to help classify the soil type from basic CPT parameters. You see, Robertson realized that there was a correlation between the cone resistance and the sleeve friction with the type of soil being penetrated. The soil behavior type chart, or SBT chart, looks like this. The measurements collected from the penetration, that is, the tip and the sleeve resistance, are normalized first to remove the influence of depth, and then the values are used to look up the soil type from the SBT chart. For example, let's say at a certain location, the normalized tip resistance and the friction ratio are 100 and 1 respectively. We can see that the projected line intersect in the zone 6. We can see that the soil can be classified as sands. Although this classification method is not accurate, independent studies have shown that the normalized SBT chart has reliability greater than 80%. In recent years, the SBT charts have been color-coded to aid in visual presentation of the SBT on a CPT profile, matching colors with the type of soil encountered. So, this is just the classification of soil, but there is more we need to know about the soil, such as the unit weight, drained and undrained shear strength, sensitivity, consolidation characteristics, and more. Just like in the soil profiling, semi-empirical correlations have been developed over the years to map CPT parameters to the associated soil properties with varying accuracies. The CPT is even capable of estimating the results of other in-situ testing equipment. In conclusion, the CPT is a versatile and highly capable piece of equipment when it comes to soil investigation for geotechnical engineering purposes. The CPT can be deployed to explore offshore sites for oil and gas platforms and wind farms. However, cone penetration tests is not a one-size-fits-all solution for ground investigations. The implementation of any type of ground investigation is a function of the proposed project and the associated risks. This table here, provided by Loon, Robertson, and Powell, presents the perceived applicability and usefulness of major in-situ tests in different ground conditions. The applicability is measured from A, which is the high side, to C, which is the low side. it is evident that the cone penetration test and its variants show a better applicability rating across different conditions compared to other in situ test types. Yes, there are some disadvantages to the CPT. A few that come to mind are the relatively high capital investments. It requires somewhat skilled or trained operators. You cannot collect soil samples during the test, and the penetration can be restricted in some gravel or cemented soil layers. So, what does the future hold for cone penetration testing? With the advent of artificial intelligence and machine learning technologies, there are studies that have been conducted on the implementation of AI to directly interpret the CPT raw data from soil classification and parameters. I will touch more on this in my next video on AI and machine learning in geotechnical engineering. If you found this video interesting, like the video and subscribe to the channel. I will see you on the next one.